Welcome back to Very Ordinary Differential Equations. In this final lecture, we study the use of a variation of parameters to find solutions to non-homogeneous linear systems. For a single non-homogeneous linear equation, so this was the form that we've seen in the past, it had complementary equation where the forcing function was 0. Suppose that complementary equation has a fundamental set of solutions y1 through yn. Finding a single solution to the non-homogeneous equation through variation of parameters amounted to assuming that yp was a linear combination of unknown functions ui times the solutions from our fundamental set yi. Then there were some restrictions placed on these, and then you solve for the ui. Well, we apply basically the same idea. Suppose you have a non-homogeneous linear system, y prime equals ay plus f, where the system involved has n functions, which is to say, y is an n by 1 column of functions, the forcing function f also an n by 1 column, and a is an n by n matrix of functions. Let's suppose that y1 through yn are linearly independent columns of functions that solve the complementary homogeneous system. That is to say, they form a fundamental set of solutions. It doesn't make sense to consider u1, y1 all the way through un, yn for columns un, however, because y1 through yn are columns, so if u1 is also an unknown column of function, there's no way to multiply a column by a column like that. So suppose you have a fundamental set of solutions y1 through yn. So these are n distinct columns that are each n by 1, and they're all linearly independent. Use them to make a fundamental matrix. So what we mean here with our notation is we've made a matrix where these are the columns of the matrix. So we have n columns, each is an n by 1 column, so we have now an n by n matrix. Then we can consider the product A times capital Y. So A times capital Y was just a matrix whose columns were given by the y sub I. Distributing this multiplication simply says the column here is given by A times this column. The next column of the matrix is given by A times the second column, all the way through. The last column of AY is given by A times the last column YN. But since we assumed that each of these columns were solutions to the differential equation y prime equals AY, we actually just end up where this is y1 prime, y2 prime, all the way to yn prime. In other words, ay equals y prime. So let's go ahead and set our particular solution yp to be that fundamental matrix y times an unknown column u. Then we need to see what has to happen for y prime to equal ay plus f. Note that dimension-wise, the product now makes sense. Fundamental matrix is n by n, and this is an n by 1 column of functions u1 through un. So we can multiply these together, but we want to see what has to be true about u for y sub p to actually solve the differential equation. So let's take its derivative. We are hoping to get out that yp prime is ayp plus f. First, let's take the derivative. We use the product rule, y prime u plus yu prime. Now that y prime is of interest because remember that y is a fundamental matrix for the system. So y prime is the same as ay. And then yu is the same as yp. So overall, yp prime is definitely equal to ayp plus yu prime. We wanted yp prime to be ayp plus f. So if yu prime is equal to f, we have a solution. So the goal is now find a column of functions u so that yu prime equals f. If you can do that, then yp equals fundamental matrix y times u is a solution. And this is really a generalization of variation of parameters from the past. So think back to how we used variation of parameters to solve higher order non-homogeneous equations. Well, we can interpret a higher order equation as a first order linear system. Specifically, suppose we have here our higher order non-homogeneous differential equation. We convert it into a first order linear system by setting z1 equals y, z2 equals y prime, z2 equals y double prime, and so forth, all the way up to zn is the n minus first derivative of y. So that gives me z1, z2, all the way up to zn. But what's zn prime? It would simply be the next derivative of y. So the original differential equation becomes this system. Okay, so this is old work. Refer back to when we first introduced systems of equations. This is how you would convert a single non-homogeneous linear differential equation into a first order system. So we have here some sort of capital Z prime, matrix A, capital Z, forcing functions. In this interpretation, a fundamental matrix of the linear system is given by the Wronskian of a fundamental set of solutions to the original higher order equation. Therefore, our technique for linear systems would actually amount to Wronskian, aka fundamental matrix, times unknown column of derivatives equals forcing function. So here we have fundamental matrix for the system, which is just Wronskian for the original, times column of unknown derivatives equals forcing function. This is exactly what you do using variation of parameters on higher order equations. If you run through all of this multiplication, you would have y1 u1 prime plus y2 u2 prime, etc. equals 0. y1 prime u1 prime plus y2 prime u2 prime, etc. equals 0. All of those zeros, but then in the last row, the n minus first derivative times u1 prime, n minus first derivative times u2 prime, all the way to the last term here gives me forcing function f over initial coefficient p naught. That was exactly what we did to use variation of parameters on higher order equations. So this new approach is completely consistent with how we've done it before. Overall, what's the technique we're going to use? If we want to find a particular solution to this non-homogeneous linear system, where you happen to already know a fundamental set of solutions to the complementary homogeneous system, construct a fundamental matrix out of your fundamental set of solutions, set y u prime equals to the forcing function f, solve for u prime. U prime is now just inverse of fundamental matrix times f. And remember, by assumption, these columns from the fundamental set of solutions are linearly independent. Therefore, this matrix is invertible. So solve for u prime is y inverse times f. Then you integrate term by term to recover u, and then your solution is given by y times u. So there's the technique. Set y u prime equals f, solve for u prime, integrate, and set yp equals to yu. For our first example, let's just find one particular system to this non-homogeneous linear system. However, we are given a fundamental set of solutions to the complementary homogeneous system. So we make a fundamental matrix by taking our fundamental set of solutions and transforming them into columns. So here we have y1 as a column, y2 as a column. So there is a fundamental matrix of solutions. Now we're going to declare our unknown column u1, u2, and we need to solve y u prime equals the forcing function. So what's u prime? It's just u1 prime, u2 prime. So just imagine that we're multiplying this matrix y by u1 prime, u2 prime, and the result should equal the forcing function t1. So in the first row, you'll end up with minus e to the t times u1 prime, plus e to the minus t times u2 prime, but that should be equal to this first row of the forcing function t. And in the second row, you'll have e to the t u1 prime plus e to the minus t u2 prime equals 1. And now the goal is solve for u1 prime, solve for u2 prime. So here we have two equations involving both u1 prime and u2 prime. If we add the two equations together, we will exactly cancel out the term with u1 prime in it. So we end up with u2 prime equals t plus 1 over 2 e to the minus t once we solve for u2 prime. If we subtract the two equations from one another, we can solve for u1 prime and get 1 minus t over 2 e to the t. And now what we've done is we've recovered u2 prime and u1 prime. Having recovered u2 prime and u1 prime, we just have to integrate each of them. And remember, we're only looking for one possible solution, so any constant of integration is fine. We're always going to pick 0. So we end up with u1 is t e to the minus t over 2, u2 is t e to the t over 2. Therefore, our solution is given by y sub p equals yu. Here was y, our fundamental matrix. Here is u. We factor out the 1/2 and just have t e to the minus t, t e to the t. T e to the minus t, t e to the t with the 1/2 factored out. Once you perform all of the relevant matrix multiplication, it's just the column 0, t. So there is one particular solution to our non-homogeneous linear system. For our second example, find one particular system to this non-homogeneous linear system, but again, a fundamental set of solutions has been given to us. So we make a fundamental matrix by transforming our fundamental set of solutions into columns. There they are. We set up yu prime equals the forcing function f, and row by row, we get these two equations here. E to the t cos t times u1 prime minus e to the t sine t plus u2 prime equals the top row of the forcing function e to the 2t. And in the bottom row, you'll get e to the t sine t u1 prime plus e to the t cos t u2 prime equals e to the minus 2t. If we cancel e to the t from every term, we just get the following. So here are our two equations involving u1 prime and u2 prime. We need to solve for u1 prime and u2 prime. Multiplying the top by cosine and the bottom by sine, you'll end up with this and this expression respectively. But notice that if I was to now add them together, we would cancel out the u2 primes, which just yields u1 prime can now be solved for. Adding these two together, notice, produces a sine squared plus cos squared, which I can ignore. So on the left, we just directly get u1 prime. And on the right, we get e to the t cos t plus e to the minus 3t sine t. Now here was our initial system. If we multiply the top by sine and the bottom by cosine, we'll end up with these two expressions, which I can now take the difference of to cancel out the u1 primes. That will directly give us that u2 prime is e to the minus 3t cos t minus e to the t sine t. So we've managed to solve for each of u1 prime and u2 prime. All we have to do is integrate each of these. Okay, it's a fairly tedious integration by parts exercise, but you'll end up with u1 and u2 respectively. Having solved for u1 and u2, we simply declare that our particular solution is the fundamental matrix of solutions that we started with, and then this column that we just solved for. So here was our fundamental matrix of solutions. Here was the column that we just solved for. If you go ahead and do the multiplication and simplify, it works out to be fairly nice. The 1/10 you can factor out just to make the matrix look a little nicer. Not so bad. For our third example, find one particular solution to this 3x3 non-homogeneous linear system. However, we are given a fundamental set of solutions again. Well, we make our fundamental matrix and then set up yu prime equals f. So make your fundamental matrix by taking this as the first column, this as the second, this as the third. Then multiply by a column u1 prime, u2 prime, u3 prime. And what we should get out, row by row, are 0, 0, and 1. Once you go through that multiplication, here are the 3 rows you get. If we add the first row to the third, we are exactly going to cancel out these u2 primes. This exactly allows us to solve for minus 2 e to the t u3 prime equals 1. And if we solve that for u3 prime, we get u3 prime is minus 1/2 e to the minus t, which we can directly integrate and solve that u3 is 1/2 e to the minus t. Remember, you can take any constant of integration you want, so why not take 0? So here's our system of equations that we started with. We've already determined that u3 prime is minus 1/2 e to the minus t. So if I take this for u3 prime and substitute it in here, we'll end up with something that we can now solve for u2 prime. If we solve it for u2 prime and then integrate, we can say that u2 is minus 3/4 e to the minus 2t. plus any constant we want, and we choose 0. Well, here was our original system. We've already determined that u3' and u2' have these known values. So if I take those two values for u2' and u3' and substitute them into the middle equation, we're now in a position to solve for u1'. Solve for u1' and integrate, and we determine that u1 is 1/3 e to the minus 3t. So we have solved for a possible choice of u1, u2, and u3. So we set u to be just a column made up of these choices. There's a common denominator of a 1/12 that we can factor out of this to simplify our presentation a little bit. Now we just have to set yp is fundamental matrix y times u. Remember that u, we had this 1/12 we factored out of it. Our fundamental matrix, remember, was just our fundamental set of solutions done column by column. Now we just have to take this product and simplify. And it's pretty nice. We end up with just a column of constants, -3/4, 1/12, and -1/4. So one particular solution to our differential equation, y prime equals ay plus f, is just this column of constants. All in all, what did we discuss? Variation of parameters is a technique that we've used very productively in the past to find particular solutions to non-homogeneous equations, and it generalizes very directly to solving non-homogeneous linear systems. In fact, everything we used to call variation of parameters is now encompassed by this one general technique. Ultimately, what you end up with is a pretty clean way to find a particular solution to a non-homogeneous linear system. However, you do need to begin with a fundamental matrix of the system. In other words, a fundamental set of solutions. So, given a non-homogeneous linear system, find a fundamental set of solutions to the complementary homogeneous system and then proceed. Assuming you have found a fundamental matrix, simply solve yu prime equals f, solve it for u prime, integrate term by term, and then your particular solution is just given by yp equals the fundamental matrix y times the column you just solved for, u.